Welcome to our lesson today on Year 10 Physics, Air Resistance and Terminal Velocity. Let's just hope that dog doesn't represent your physics career. Alright, let's have a think. If everything falls at the same rate as it does, which is g, the force of gravitational attraction, does that mean everything actually is falling at the same rate? Even if we have different weights, yes it does. If we have different sizes, yes it does. Even if they're in the different shapes, this is where the misconception starts to come in. The acceleration due to gravity, which we refer to as g, or 9.8 meters per second squared, is the same for every object. But what tends to get in the way is the shape of them. Things that are like a piece of paper that have a very large surface area and have a lot of air resistance are not going to fall at the same speed as, say, when it's crumpled up into a tiny little ball and there's less air resistance on it. If we look at a vacuum, then that doesn't apply. Everything will fall at exactly the same rate then. So, what's our task today? We're going to look at the concept of air resistance and terminal velocity. Don't fall over like that lady there. Air resistance and terminal velocity is where we're heading. And you should be able to just, by the end of today, explain what free fall is as objects fall through air. When we talk about air resistance, we're talking about an object moving through air, which is a gas. Now, gases and liquids we refer to as fluids. A fluid is an object that is a little bit runny in some way. It's just like gases are a lot more runny than a liquid, but they behave in similar ways, and that's why we grouped them together as a fluid in physics. When an object's falling through that, such as this diagram on the left here, you can see the air as it's trying to rush around, and there's that high pressure bit in front of it, on the front side here, and a low pressure area on the back side there. And that low pressure there at the back there causes all these sorts of air currents that flow around in the back here. And it's almost like as your object moves forward through the air, it's got to pull all of this stuff behind it along with it. And that's what we refer to as the force of drag, which I've shown there as a vector quantity. Because it is a force, it has a magnitude and a direction. So the F stands for force, the D is drag, and the little arrow on top means it's a vector. So it's acting as a force in a certain direction. When we consider that air is the fluid that we're dealing with, that's where we call it air resistance. So there's a reason we refer to it as air resistance, because it is a subset of drag through any fluid. And this force, as we said, is the pressure differences between the leading edge and the trailing edge of an object. If we look at that a little bit differently, we've got three examples there, and essentially it is the shape of an object is one factor which determines how much air resistance we have. If we're more aerodynamic, there's less air resistance. And if we take that even further, an airfoil is designed to have very little air resistance as the air flows around it. So if we look at the top example there, up here, this red one, you can see the air is running around. There's a certain amount of friction between the air and the object as it flows over. As the shape changes, such as in our second one here, you can see there's this almost this flatter area at the back here, which causes that low pressure and all that turbulence there. And there's a lot of kinetic energy in that, and there's a lot of air moving around there. That as this object, if the object's moving that way, or if the air's moving that way, it's the same thing. There is all this pressure at the back here that creates that air resistance and stops the air flowing smoothly over and would stop the forward motion of that green ball. But as we've shown down the bottom here, if we design the object correctly, the air should flow around evenly around either side, and you can see that this turbulence at the back here is greatly reduced, hence there's a lot less air resistance. And notice that you have this air that hits directly on the front there that is going to directly provide your backwards pushing force. So obviously the smaller this surface here at the front edge and the more sort of aerodynamic it looks, the less is that actual pressure at that point there. So factors that which start to affect our air resistance, we've got the size of the object. So obviously a larger object is going to have a larger surface area, more air to push on it, more air to pull behind it, so more drag. The density of the fluid that we're going through, so air and water, you've tried to run through air and then run through water, and you probably notice the difference between those two. And obviously the velocity, because the force of drag is directly proportional to the velocity squared. Now when an object's in free fall, obviously falling down, such as our person here, who's falling through the sky, so we'll make him look upset because he's falling at the moment. What we have here is our weight down the bottom, the force of weight, which is mass times gravity, and we have the drag or the air resistance the other direction. Now my little question here in the pink cloud, what is the result of these unbalanced forces? If we have a look at there, we know they're unbalanced forces because the drag, the arrow for the drag, as in the physical size of that arrow, is much, much less than that arrow. This one's bigger, hence it's going to be pulling it down in that direction more. If the two were balanced, that's a different scenario. But one's bigger, so he's going to net move in one direction. He's going to accelerate. And if we think about our net force, the net force, that's written the same way, as the same thing in two different ways, is the weight minus the drag. We think of it in those terms. What is the resolution of those two vectors? As we subtract these two together, what do we end up with? But in that scenario, so our man's falling, but he's having fun now because he's moving really fast. So what happened? This force of weight hasn't changed. What's changed is the drag, because what actually changed was his velocity. This is a force that is acting on the man as he falls, man or woman, it doesn't really matter. That will cause him to accelerate down, and he will continue to accelerate until both of them are equal. And that's what we refer to as our terminal velocity. The force of weight equals the force of drag, or written a different way, when we add them together, they add up to 0. Because it's almost like if you think up is positive, so that's a positive force, down's a negative, that's a negative force. So if I add them together, it's a net force of 0. All right. So that's what we're referring to on the side here. At some point, the drag increases till it equals the weight, and then they're balanced. Further acceleration cannot occur. This is terminal velocity. His velocity will be constant. We look at the motion of this car. There's an acceleration to the left there going forward. There's the force of drag going backwards. So we could say that the car is being accelerated forward, whilst at the same time experiencing drag to the rear. They're balanced. One isn't bigger than the other. So what's going to happen to the car's velocity? It will be constant. He's traveling at a constant velocity. That just means that there is no net acceleration. If he took his foot off the accelerator, this force would decrease, would be less than this force, and hence he would start to slow down. So if we think about an object in free fall, not that sort of free falling, that's different. So this man's falling down in free fall, and when the forces are balanced, that means this one down here is the same as this one up here. That means that he is traveling at a constant velocity. So the velocity is constant. That could also mean that if he was sort of sitting at rest, there is no net force pulling him down, hence there is no real drag on him. So when we're traveling at constant velocity, we have to be careful about what we mean, because constant velocity means you're either traveling at a speed or a velocity, this guy here is falling down, or your velocity is 0, because that is also a constant velocity. And that's the two options for balanced forces. You're either traveling at a speed or a velocity, or you're traveling at a velocity of 0. Let's look at this question here, extend what we're going on here. What's changed about the free fall of this particular person with the parachute? Obviously, the parachute's changed, but from a physics point of view, we have a much, much larger surface area for that air resistance. Okay, so when we think of our terminal velocity, the weight equals the drag, but in the case of the parachute, we massively increased the drag and that will change what our terminal velocity ends up being. So the actual force of weight hasn't changed, but the drag has increased, which will lower our entire velocity. But in the end, we'll end up with terminal velocity where the net forces are zero, as in the weight going down and the drag going up are going to end up being balanced because we've changed how the drag's operating, which changes our final velocity. Here's an example of what's happening. So this man's jumping out of our helicopter. He has the force of gravity of 833 newtons. Remember, mass times acceleration. The acceleration is 9.8 meters per second squared. Forces are measured in newtons. When he jumps out of the helicopter, that is the only force acting on him, so he begins to fall. But as his velocity increases, the force of drag starts to increase and increase and increase until they're equal to each other. So we can say the net force is positive 833 minus 833, which is 0 newtons, which means terminal velocity acceleration is now 0. Good example of this is the International Space Station. This one's been around a little while. It was a joint project started way back in 1998, so over 20 years ago. The first crew took up residence there just on about 20 years ago now, as I'm recording this. Nice big laboratory that is continually being expanded up in space as more modules are added from different countries and so on to improve the whole overall effort. And it's the 4th space station to orbit Earth. There was a couple of notable ones that the Russians had quite some time ago, but this is sort of the major one now that is operation because it's an international effort and it's quite large. People aboard the space station appear weightless, a bit like this particular astronaut appears weightless up in space. They float around like there is no gravity. However, they are still within the gravitational field of Earth, so gravity is still pulling on them. So the question becomes, why do they appear weightless? It's because of this idea of free fall. Think about the object, think about the situation of this cannon here, shoots a cannonball out with a certain velocity and slowly it gets pulled down towards the Earth. At point A there, it lands into the Earth. If we shoot it out a bit faster and it travels with more forward velocity, we can get it further and further. And then if we get to the point where the rate that it falls from the cannon down to the ground matches the curvature of the Earth here, we end up with path D here, where it will stay in free fall. When engineers and scientists launch satellites, they will manipulate the orbit of a satellite, but they want a lot of sideways motion to make sure that the rate that it falls to the ground matches the rate that the ground falls away from it, as in the curve of the Earth, and it stays in orbit. But you can see from other orbits, if we give it a little bit more, we can adjust the height that it is from Earth. So like the space station, things are in free fall because they're actually falling. They appear weightless, but it just means they're forever falling because the amount that they move sideways is so fast that as they fall down, the Earth keeps curving away from you and you never ever reach it. You never ever hit the ground. And so hence the concept we have in physics is the frame of reference. So the weightlessness is all to do with the frame of reference. If you're just looking inside the space station like this here, it looks like they're floating, they're totally weightless. But if you look outside that, you'll see that the space station is actually moving. When you have a different frame of reference, which is Earth instead of the space station, you can see that gravity is still there, you're just falling constantly. Exactly like an amusement park ride or something like that that's dropping you down. I encourage you to have a look at this crash course video on distances. It's worth checking out. And that brings us to the end of today. We discussed air resistance, we discussed terminal velocity, and you've seen some examples of it, so you should be able to explain it now. Thank you for coming.